Professor Michal Irani will talk about deep internal learning, deep learning with zero example.
Hi, everyone. I hope you can see my screen. I hope you can see my slides. If not, please shout. So I'd like to tell you about something we've been working on in my lab in the past 3 years, something that we call deep internal learning. What I mean by that is how we can train a deep network in a totally unsupervised way without ever having seen any prior example by training on a single image, the test image alone. Why is this interesting? Well, we're all used to external learning. That is to say, we train a network on many, many external examples, train it for hours, days, and then keep it frozen, and then give it new test data. And this, of course, does amazingly well, but what happens if we don't have enough training examples? Or what happens if the statistics of our test data is out of the distribution of the training data? In those cases, deep learning fails miserably. And what I'd like to show you is how we can often overcome these problems by replacing external learning with internal learning. And this paradigm gives rise to lots of applications, including super resolution in images and videos, image dehazing, segmentation, transparency separation, retargeting, and more. Unfortunately, I'll be able to show only a small subsegment of these things, both because we have a short time and because I want to leave the last few minutes to show you something different, what we call work we've been doing in mind reading, how we can decode brain activity, reconstruct images from fMRI. So let's start. So how can we train an image? How can we train a deep network on a single image? Well, it turns out that there's a lot of redundancy inside a single natural image, both within the same scale as well as across different scales. When I say within scale, I mean that if you see a small patch once inside the image, you'll almost surely see it many more times inside the same image. Now here I'm showing you relatively large patches, but in practice I'm talking about much smaller patches, 5 pixels by 5 pixels or 7 by 7. And this has been used by us and by many others for a wide variety of applications, including image completion, image denoising like non-local means, BN3D, visual summarization, and much more. Less commonly used, but very strong, is the recurrence of information across scales in the image. That is to say, if I take the image and scale it down, then almost any patch in the original image will almost surely find an identical patch to it in a coarser scale of the image without scaling down the patch, which means the tiny pattern appear in multiple sizes in the original image. And again, I'm showing it here, displaying it for large patches, but I'm talking about much smaller patches. And this property, again, has been used by us and by others for lots of applications, including fractal image compression, super resolution from a single image, blind deblurring, blind dehazing, and much more. Now, this may look like a very contrived image to you with lots of repetition, but it turns out that if we go to small enough patches, as I said, 5 by 5 or 7 by 7, this recurrence is true for almost any patch in almost any natural image, be it indoor, outdoor, man-made, natural. You don't have to see perspectivity. You don't have to see in your own eyes the repetitions. And we showed this empirically in our 2009 paper. So the nice thing about this property is that it allows for totally unsupervised algorithms. They require nothing but the test image alone. Okay, the internal repetition of patches give all the information needed to solve very ill-posed problems. The bad news is that in the past few years, these methods have been totally outperformed by deep learning methods, which is really depressing. So for a long while, I was walking around with this uneasy feeling. On one hand, we have this very powerful tool, deep learning, which does amazingly well, but is extremely data hungry. It requires tons of training examples, and we don't really understand what it's learning. On the other hand, we have this nice internal redundancy property. We physically understand it. It's totally unsupervised, doesn't require any other examples, but doesn't perform as well as deep learning. So for a while, I was asking myself, is there a way to combine the power of these two complementary approaches? And luckily, 3 years ago, my student, Subsampling, came up with a brilliant idea of doing deep internal learning. That is to say, let's train an image-specific CNN at test time on examples extracted directly from the test image. And as you'll see shortly, this can be done quite efficiently. So the first problem we looked at was how we can apply this to super resolution. In super resolution, we have a low resolution images, and the goal is to generate a high resolution image with higher pixel density. But each pixel in the low resolution image is, of course, a weighted average of some pixels in the high resolution image, which induces this linear relation between the high resolution image and the low resolution one, a blur with this blur kernel and subsampling. Now, even when the blur kernel is known, this problem is ill-posed because we have more unknown pixels than the ones we have in our low resolution image. The problem becomes much more complicated when the kernel itself is also unknown, in which case this is known as blind super resolution. Now, I won't review all the super resolution literature, but by far today's leading methods are deep learning ones, and the most common ones are external super resolution methods. And their idea is, let's train a network on lots and lots of training data, training examples, low resolution, high resolution image pairs. We'll take a network, we'll input a low resolution image, and we'll have to learn to output the correct high resolution image. And we can train it on as many images as we want, because all we have to do is take high quality images, downscale them, and we have such pairs of low resolution, high resolution images. So these networks are trained for hours or days, and then once trained, they are applied to new, never before seen images, and out comes the super resolved image. And this does amazingly well. In fact, these networks gave about 2 dB improvement in PSNR over anything that existed prior to deep learning. However, when Asaf and I started looking at it, we realized that these networks work well only under ideal conditions. And when I say ideal conditions, I mean that there's a fixed known ideal downscaling kernel. Okay, remember, we said we can generate those low resolution images by taking high resolution images and downscaling them. These data sets, typically, the downscaling is done with an ideal low-pass filter, or something close to an ideal, like bicubic downscaling. But hey, the world is not ideal. When I take a picture, I slightly move my camera. That's not an ideal low-pass filter. And the next picture I'll take, I'll move my camera slightly differently. It'll be a different low-pass filter. So these low-pass filters are image-specific. And once you give them to these networks, and they're out of the distribution of what they've trained on, they don't perform any better than interpolation, and you'll see this shortly. Worse, they assume that there are no artifacts in the low-resolution images, no sensor noise, no JPEG compression, and in the presence of those, they perform quite poorly. So we said, let's solve these problems by replacing the external learning with internal learning. We call it zero-shot super resolution. This appeared at CVPR 2018. And the idea is very simple. Here is our low-resolution test image. That is the only information we ever saw. We've never seen any other image in our lives. What we'll do is the counterintuitive thing. We will downscale this image to generate an even lower resolution image. And now we will train a very light image-specific network to bring this image back to its original resolution. And this is the loss. You have to recover back the original low-resolution image. Once this light network is trained, we can apply it to the original low-resolution input image to generate the high-resolution output image. And the rationale here is very simple. Because we have the strong recurrence property of patches across scales of the low-resolution image, whatever network is good for increasing the resolution of the patches in the small image will also be good for increasing the resolution of the patches in the original low-resolution image. Now, of course, training a network on a single example is stretching it too much, so we'll generate multiple examples from this single image by augmenting it. We'll flip it, we'll rotate it, we will scale it. This will generate hundreds of images, all with the same patch distribution with which we can train this network. And this generates an image-specific network. Now, you can, of course, ask, well, how can a network be trained at test time? It turns out that because this is a very light network, all it has to learn is to increase the resolution of this particular patch distribution, no other image in the world. Therefore, it can be realized with a very small network and trained, and it takes 9 seconds on a V100 GPU, both the train and the inference time, and this is regardless of the image size. Now, what about the downscaling? We said that this is also image dependent. Remember, we said that each image was generated with a different low-pass filter. Well, it turns out that the correct downscaling can also be estimated directly from the low-resolution input image itself. This is something that Tomer Michali and I showed in our paper in 2013. And more recently, we showed how this can be done using deep internal learning, a work with Sefi Bel-Kliegler and Asaf Shocher. We call it kernel GAN. Okay, we're able to recover the correct downscaling kernel using a GAN trained internally on the low-resolution image itself. And there's a recorded talk, a VOD talk by Sefi Belkligel in the GAN session immediately after my talk. So I encourage you to go listen to it. And the idea is that the correct downscaling kernel is the one that will also maximize the recurrence of patches across scales in this image. Tomer and I showed an analytic proof for that, and now Sefi can show you in his talk how we can do this using an internal GAN trained on a low-resolution image. And this really gives us super resolution in the wild. We can super resolve any image of any data type, any kernel, any scale and aspect ratio. The network will adapt itself to the particular low-resolution image. So let's look at results. So here is a low-resolution image. We have no idea how it was generated. It was downscaled with a non-ideal downscaling kernel. Here's what happened if you just interpolate this image using a regular bicubic interpolation. And here is the result with the state-of-the-art, externally trained EDSR+. And if I flicker between those two images, you'll barely see the difference. Now, it's not that EDSR+ is not good. It's amazingly good, okay? But it's good for upscaling the images that were downscaled bicubically. But this image was not downscaled bicubically. It's outside of the training set of the, outside the training distribution of the EDSR+, so it doesn't perform any better than interpolation. In contrast, here is the result of the internal learning with the ZSSR. And you can see the big difference, okay? This is internal, external. And you can see that we can recover the fine details that external training was not able to do. And the reason zero-shot super resolution internal learning is able to do this is because it's adapted to the image-specific degradation, the image-specific downscaling, and the image-specific recurrence of patches. Here's another example, an old photo downloaded from the internet post-World War II, Checkpoint Charlie. We have no idea how it was generated. Here is regular interpolation. Here is the result of the externally trained super resolution. If I'll flicker between the two, you'll barely see the difference. And here is the result of the internally trained super resolution. And again, if I'll flicker between the two, you'll see the dramatic difference. Note the difference in the legs here. Okay, you can see we can really recover with the ZSSR information that is smaller than a pixel size. We can go beyond the Nyquist limit simply by using the correct image-specific degradation and the correct cross-scale recurrence property, or look at the back of the motorbikes here. Okay. And what happens about noise? Well, here is an image downscale, which is JPEG compressed, a low-resolution image. Here is the result of the externally trained super resolution, and you can see that it super resolves both the signal and the noise. It doesn't know them. It cannot tell them apart. Where in contrast, here is the result of the internally trained super resolution, and if I'll flicker between the two, you'll see the dramatic difference. How come we get rid of the noise? Well, it's very simple. The signal patches, they do recur across scales in a natural image, but the noise does not. So ZSSR, the internal super resolution, learns how to generalize for the signal, but it doesn't know what to do with the noise, so it doesn't do anything with it. And we've, of course, checked it on other types of noise, speckle noise, Gaussian noise, and you'll see this, and the same thing happens. We also empirically evaluated the algorithm, compared it to external methods. So on ideal images that are downscaled ideally and have no noise, yes, external training does better than internal training. But we do reasonably well. I mean, that's their bread and butter, but we do reasonably well. But on images which are non-ideal, and that's what real images are, we do 1 or 2 dB better than the state of the art. But this, of course, requires knowing the correct image-specific kernel, and I encourage you to listen to Sefi's talk in the GAN session immediately after my talk. So far we saw how we can use it on images, but it turns out that deep internal learning can also be used on video. For example, I showed you super resolution, spatial super resolution in image. It turns out we can use it to do temporal super resolution in video. What do I mean by that? Well, in spatial super resolution, the goal is to increase the sampling rate inside an image. In temporal super resolution, the idea is to take a low frame rate video and generate a high frame rate video from it. For example, move from a 25 frame per second video to a 200 frame per second video. But we don't want to just stretch the information. We don't want to just interpolate in time. We want to be able to recover dynamic information that occurs faster than frame rate, that is invisible in the original input video. We want to go beyond the temporal Nyquist limit. We want to be able to undo motion aliasing and motion blur. For example, here is an example of motion aliasing. What you see here is a fan that is rotating faster and faster clockwise, but at some point, it will appear to be rotating counterclockwise. Now, I don't know if your internet is fast enough to see this, but that's motion aliasing. Another effect that happens when a very slow camera records a fast scene is motion blur from the moment the shutter of the camera opens until it closes. The fan moved a lot and got smeared. Note that these effects cannot be undone using by playing in slow motion or doing temporal interpolation. Temporal interpolation will not help to undo motion aliasing and motion blur, no matter how sophisticated the interpolation is. This can only be done using temporal super resolution, and this is a dramatic difference between temporal super resolution and temporal interpolation. So our idea is very simple to the zero-shot super resolution in images. We extended to space-time, but the sophistication comes in the augmentation we apply to the test video. And I'll visually show you two very useful augmentations. You can find many more in our paper. By the way, this was published at ECCV 2 months ago. I worked with Liad Polak, Eyal Naor, George Pisha, and Shai Pagon. And one of the very useful augmentations is subsampling the video in time. Okay, this is done by blurring and subsampling in time. The frames remain the same size. So if this was the original video and the original temporal scale, in a coarser temporal scale, you'll see the fan rotating faster with more motion blur. In a yet coarser scale, you'll see already motion aliasing and much stronger blur. In other words, by generating coarser and coarser temporal scales, we're actually synthesizing the same dynamic speed as seen, but with higher speed, more motion blur, and more motion aliasing. We can now train a video-specific network using these pairs of examples to learn how to undo the motion blur and motion aliasing for this specific dynamic scene. Once trained, we can apply it to the original input video to generate the desired high-resolution output video, high resolution in time. So this is one very useful augmentation. Another very useful augmentation is based on our new observation that space-time patches in video recur not only across different spatial temporal scales of the video, they also recur across different dimensions of the video. What do I mean by that? Well, here's the space-time volume of the video, x, y, time. If we just take spatial slices of this volume, then we'll see the frames that we're all used to seeing. But if we now take this volume and rotate it such that one of the spatial axes coincides with the temporal axis, okay, and now take slices of this, we will now see space-time slices of the video. Interestingly, note that these space-time slices have a lot of resemble in similarity to the original video frames. Only they have one big distinction. They have aliasing along the temporal dimension. So we can use the high resolution, the non-aliased information in the spatial frames in order, as high resolution examples, to resolve the aliasing in the temporal dimension in the space-time slices. And you can find much more details in our ECCV paper, as well as on our website. So let's look at some results of super resolution, increasing the frame rate by a factor of 8, moving from a 25 frame per second video to 200 frame per second video. What you see here is the fan video that I showed you before. At the top left is the input played in slow motion. You can see here NVIDIA slow-mo, Dane, flawless. They're all externally trained, and you can see how horribly they do. And in contrast, this is our internally trained super resolution, and you can see that we resolve both the motion aliasing and the motion blur. Here is another example, a rotating disc. You can see here the input video played in slow motion. Once again, NVIDIA slow-mo, Dane, flawless. They try to increase the frame rate, but they do a poor job. And here is our result. And you can see it's not perfect, but we're able to mostly undo the motion aliasing and motion blur. Of course, the motion doesn't have to be repetitive. Here's a single jump, flip in the beach. And you can see, look at the legs here. This is the original input video with the motion blur, NVIDIA slow-mo, Dane, flawless. Ours, in this case, there's also ground truth. And of course, it doesn't have to be circular motion. It can be chaotic motion. These are diamonds falling down. Again, this is the input video at the top left. At the bottom right is the ground truth. You can see that the competitors contain lots of motion blur, and this is our result. And we have many more examples on our website with complex dynamic scenes, splashing water, flickering fire. It doesn't have to be clearly repetitive motion. So far I showed you how we can use deep internal learning for doing super resolution in images or in video, and this generates an image or video specific CNN. The nice thing is it's totally unsupervised. It requires nothing but the input image or video. And since it adapts to the unknown image-specific degradation, it also leads to state-of-the-art super resolution on real non-ideal images. But can we use deep internal learning for other things? For example, for segmenting an image into a foreground and background layer, for dehazing an image, for taking an image and separating it into its reflection and transmission? The answer is yes. All of these tasks can be solved using deep internal learning by training on the single input image alone. Now, we actually showed that all of these can be solved on a single unified framework using what we call double dip. This was a CVPR 2019 paper together with Yossi Gandelman and Asaf Shocher. Unfortunately, because of the short time, I cannot show you this. I just please refer to this paper if you're interested. I'd like to use the last few minutes that I have in order to show you a different line of work we've been working on, mind reading, how we can decode images from brain activity. A preliminary version of this work appeared in Europe's 2019, a few months ago, led by Roman Bailey and Guy Gaziv. And in the last few months, we had a significant progress in this with Niv Granot, and we're now turning this into a journal version. So let me tell you about this. So the idea is we have a person lying in an fMRI machine watching images, and we record his or her brain activity. And then we look at the area of the visual cortex. And the question is, can we use the fMRI recordings in the visual cortex in order to synthesize back the image that the person saw, as well as classify it, say what it is? Now, of course, this is not a new problem. People have been looking at this over more than a decade. People like Gallant, Kay, Naselaris, Kamitani. They were looking at pairs of images and their fMRI recordings and trying to see whether they can find a mapping, a decoding from the fMRI to images. Initially, this was done using linear regression type of methods, and the last few years, deep learning type methods have also been introduced to this problem. But there's a big problem. There's insufficient training data. These data sets typically contain 1,000, 2,000 pairs of images in fMRI, and that's because you cannot put a person for that long in an fMRI machine. And you can't use different people because the information differs from brain to brain, and it also suffers from very poor signal-to-noise ratio and very poor resolution. So this really limits what these methods can do. But we said, hey, let's use self-supervision. What do I mean? Well, of course, we're going to use the supervised training data. And the data set we used has 1,200 such pairs of images and fMRI recordings. We're going to use these, but we're going to train two types of networks. One is a decoder that learns to decode fMRI into images, and another is an encoder that learns to do the other operation around, encode images into fMRI. Now, this alone, of course, will not do the job. 1,200 images cannot span the space of all natural images. This decoder will overfit the training data that it learns to decode, but it will not be able to generalize to new images that it never saw before, okay? Or fMRI new images that it never saw before. But here is where the trick comes here. Let's use self-supervision. What we do is we stick those two networks back to back. And now, note that this joint network, its input is an image and its output is an image. And if the two networks are trained well, then the input should be identical to the output. And we can train this on images for which we don't have any fMRI. In fact, we can train it on as many images as we want. We've trained it on 50,000 ImageNet images. And this allows us to be able to train the decoder to decode images for which it's never seen in the fMRI. And this allows us to adapt them to the statistics of natural images. But we can do much more than that. We don't just ask for the images to be the same. We actually enforce perceptual similarity between those images. That is to say, when fed into a pre-trained VGG network, we request similarity of the corresponding deep features. And this allows us not only to recover never before seen images, but also adapt to never before seen classes and be able to classify those images directly from fMRI, even though the person never saw these classes inside an fMRI machine. But we can do even more than that. We can add another type of self-supervision. We can switch the order of those two networks. Note that now this combined network has an input, which is an fMRI, and an output, which is an fMRI. And if trained well, those should be identical. And we can train it on fMRIs for which we don't have any images. In fact, we can train it on the test fMRI that we wish to decode. And this allows us to adapt the networks to the statistics of the test data. So training on the test fMRI here is very, very crucial. And combining all these losses together allows us to outperform state-of-the-art, both in image reconstruction and in classification from fMRI data. So what you see here are all the 50 test images from this data set. There's no cherry picking here. This is the entire test data set. What you see in each such pair, the left side is the image that the person saw in the fMRI machine, and the right side is what we've recovered, our network recovered from the fMRI of the person. And you can see the golden fish here. You can see the llama here, or this airplane. You can see the outdoor scene, the cheetah. Look at those two people in a boat, or this beer glass, a fly, a snowmobile. Of course, not everything is perfect, but we're really excited about this. And we were even more excited about our new ability to also classify information directly from fMRI. And I want to point out that the 50 test classes and those 50 test images, they're disjoint to the 150 train classes that the person saw in the training images in the fMRI machine. So these are totally novel classes, okay? Yet we're able to classify them, and moreover, we're able to classify them against 1,000 ImageNet images with reasonable, not as well as, of course, natural images, but very impressive classification abilities. And I encourage you to go see Guy Gaziv's poster, which is poster 162 in IMVC, and he'll show you all our classification results, including numerical results, and we'll give you much more details if you want to learn about this. Somehow my PowerPoint has gone away. Where are my slides? Can you see them? Can you see my slides? Okay, to summarize, I hope I've convinced you that there's a lot of information to do internal learning, which gives rise to image-specific CNN. The nice thing is it combines the power of deep learning with internal image-specific priors. It's totally unsupervised. It needs nothing but the input image and video, and it adapts itself to the unknown imaging conditions and degradations of the individual test datum. And this leads to state-of-the-art results in super resolution of real non-ideal images, but it also allows us to do image dehazing, segmentation, transparency, separation, data retargeting, things I didn't have time to show you, but you can look at our papers. The first part of my talk, which I talked about deep internal learning and super resolution deep internal learning, is work with Asaf Shucher and Sefi Belkligler on super resolution from images, and work on the temporal super resolution videos with Liad Polak, Eyal Naor, George Pisha, and Shai Bagon. The last part on the fMRI is work with Guy Gaziv, Roman Bailey, Niv Granot, Asaf Hugi, Tal Gulan, and Francesca Strappini. What's next? Well, can we combine the power of internal learning with external learning, not trained from scratch each time we get a new signal? There's new initial work on these lines from Rajagiri's group, and I believe this is possible. Can we apply deep internal learning to other types of signals, audio, medical imagery, EEG? In fMRI, can we combine information from multiple brains? Can we extend it to decode video information and not only images, and thereby be able to read dreams? These are all things we're looking at, and I'm sorry if I took more time than I should have. I'll be happy to take your questions.
Thank you, Michal. Thank you for sharing with us the exciting work. We have many questions, actually, and we can ask only 3 questions. Let's start from the question of Lee Zelnick-Manor. Sorry. your idea is to use cross-scale redundancy or self-supervision is beautiful. Are there other redundancies within images that you think we should be using for self-supervised?
That's a good question. It's for a good reason I took Lihi as a student many, many years ago. It's a good question. I believe there are other types of redundancy, but and probably redundancies of information that not necessarily we can see. I believe definitely deep features, things like you've been doing, but I don't have a straight immediate answer at the top of my head that I can give you straight ahead.
Okay. Next question is from Aviv Meron. Does it mean you need to calculate ZSSR from scratch for different images?
Right now we do. As I said, the idea of combining internal and external learning, what I discussed at the end, is how you can employ information from multiple images and still be able to adapt at the end towards the specific image. But remember that each image does have its own unique downscaling kernel. It will have to have an additional adaptation. But I believe that there is no need to learn from scratch each time, again and again.
Okay, and the last question is from Tzachi. What prevents the encoder and decoder in the fMRI scenario from converging to a trivial network?
That's because we use all 4 losses. Can you share the screen again? I don't know if this is possible. If so, I will go to that slide. We had 4 different types of, we had training the decoder alone using training examples, which is input comes, in comes fMRI, out comes, okay, yeah, I see you shared my screen. So, okay. We use all these losses simultaneously. So the decoder is always trained in each batch. It gets both pairs of fMRI and images, as well as pairs of image and image for training the combined network, and pairs of fMRI and fMRI for training this combined image. So it has to satisfy all these losses simultaneously. So it will not be able to converge to a trivial solution, since it's required to be able to work well on fMRIs also.
Okay.